Hello everyone, so today we're gonna solve this problem, minimum height tree. So basically what is happening here, there is one tree given just like this. You can see these examples, right? So here you can see 0 1 2 3. These guys are basically graphs actually. So these trees are the tree like graph. So basically what I mean to say tree like graph means there is no possibility of any cycle. Okay, so that is why we are calling them tree like graph. So the question here, we have to basically find, see there are, for example here there are 4 nodes 0 1 2 3. So we have to treat every node as a root and find the height of it, and accordingly we have to check for all of them and we have to find the minimal height. So basically those who has the minimum height, that list we have to basically return. So for example here, if we take 1 as root, then the height is 1. If we take 2 as root, then height is 2. See here 1 and 0, so height is 2. Similarly for 3 as well, height is 2. Similarly for 2, but for 1 the height is 1. So minimum height is when the root is 1, so we have to return this one. So this is what we have to do in this question. Now let's understand what is the intuition behind the solution. Before just particularly solving the problem, let's think about the intuition of it. So the intuition is, let me draw a diagram. Okay, so you guys know mathematics, centroid stuff. So suppose we have a triangle like this, right? And if we draw a line from middle point to this node, similarly from this line to this and this line to this, then there is a point of intersection, right? This point of intersection is actually called the centroid, right? Similarly, so centroid is nothing but when the distance of nodes are same from this point, right? So similarly, the centroid of graph, a graph also can have the centroid. Okay, so for example, let's say we have a graph like this, and suppose there are other guys connected with them. So in this case, what will happen? We have the 3 centroid. See this guy as well as this guy as well as this guy, because all of them has the height as 1 if we take them as if we take them as root, right? So we have the centroid here, we have 3 centroid here. But in case of a graph like binary tree, we can have at max only 2 centroid. Why? Because in a graph like tree we don't have any cycle, right? So for example, if we have like this, if we have a binary tree like this, how many centroid we have? We have only 2 at max. So let's say we call it 0, we call it 1, we call it 2, we call it 3, we call it 4 and 5. So here you can see, if same question were asked for this question as well, we can see if let's say 4 is our root, in that case what would be the height of it? If 4 is our root, the max height would be 2 here, right? Till here. Okay, let me make it colored. Yeah, so 1 is this, 1 is this, then this would be 4. So if root was the 4, then height would be 2 only. Okay, similarly for 5 node as well, the height would be 2 here. One edge is this and one edge is this. So these 4 and 5 are basically the centroid here. So as I told you, we cannot have more than 2 centroid. Now you might have question why I am saying blindly that this cannot have more than 2 centroid. So I will tell you. Let's say if there is third centroid as well. Suppose if there is a third centroid, in case let's say there is another node like this and this also have like this. Okay, so to make this centroid, we have to, these guys we have the joint, right? There should be connection. Then now this can have the 3 centroid, but I said a tree can have only two centroid. But in this question it is clearly mentioned that there is no cycle. But if look at here, but there is a cycle here. Here is a cycle. If we want, if by any chance we want to make it that there could be 3 centroid, let's say 4, 5 and 6. So these are 3 centroid, but now this is a cycle, but cycle is a contradiction, right? So now what we can do is we can clearly understand that any tree which is any graph which is a tree like graph, they must not have any cycle. So in this case they can have at most only the 2 centroid. Okay, so this assumption we will use. So now what we will do in our algorithm, so take an example, let's say, let me draw a clearer graph to make it crystal clear. Can you guys see this graph? So it has total 9 nodes, okay, 0 to 9. Now you can see there is something which I have made red, right? But these are the normal edges only. But here's the trick. Why I have made these red? Because these are the guys which has only the one edge, right? They don't have more than one edge. 6 is only connected to 5. 3 is only connected to 5. 8 is only connected to 2. As seems like 7 and 9 as well. So here what is happening, the intention is if we treat these leaf nodes as a peripheral nodes. Okay, so let me consider this is a tree and this is a circle. Let's say I'm making a circle kind of thing. Then every node, leaf node would be on the perimeter, right, of that circle, correct? So see here, all those leaf nodes are on the perimeter of this circle. Now think about a situation, we are finding the minimal nodes, those trees which are making the minimal height. So those nodes which are nearest to these leaf nodes should be our answer. This is our intention here, our intuition for this problem. Now what happens next is, if I delete all these leaf nodes from this one by one, so leaf nodes are basically the one which has in adjacency only one edge is there. So basically the size would be 1 of their adjacency list. Okay, so if I delete them, then we would have, these are the new guys. We will make some new leaf nodes, right? If I delete them, then this is our new leaf node. This would be our new leaf node. This also would be our leaf node. This would be our, so these guys would be our new leaf node. Here these things, right? And this also. Now our intention is, after deleting this, we should be remain, as I told you initially, that in any tree like graph we can have only maximum 2 centroid. Okay, so if we see here 4 and 5, okay, these are the 2 remaining centroid we have. So these two, when we have left with these 4 and 5, these 4 and 5 should be our answer, because in any tree we would have at max only the 2 or less than 2. It could be 1 as well, or maybe 0 as well. So we have to only find these 2 centroid of array of this not array, sorry, for this graph like binary tree, and that should be our answer. So this we can do, and you remember we are doing in topological way. See here, all the leaf nodes we are deleting, then we are making the new leaf nodes, and then finally we would be till the size raised to 2 only. So till the time we have greater than 2 size, we will keep on deleting the leaf nodes. Once we have less than or equal to 2 size of that adjacency list, then we would be stop, and whatever is remaining, that would be our answer. So we do same way in the topological sorting. So we will use that method only. So let me quickly write the code of it. So guys, first of all, what we are doing is, first of all, we are making the adjacency list here. Okay, so I just created the adjacency list is here, which is basically of size n. So I have created an integer of an array of the hash sets. Okay, this is basically this ADJs in array of the hash set. Okay, so I am assigning them here. ADJ is equal to new hash set of size n, and I'm just taking one leaves array list, which will be, this is just a variable, we will use it later part. So one thing I'm checking here, if n is equal to 1, right? So if n is equal to 1, then we don't have any other choice, we will definitely only return this guy. So would we add that 0 and would be returning. So till here it should be fine. Now what I'm doing here is, in this line I'm just initializing the adjacency list with a empty hash set, because we need to avoid the null pointer exception. Then I'm making here the adjacency list, so that age is given in the in this you can say here, this age is, this array is given here, so I'm using. So what I'm doing is, basically for every age we have, this is a bi-directional, right? If 0 is in the adjacency list of 3, then 3 also in the 0, so I'm adding both of them, right? So ADJ, I'm adding 0 with 1 and similarly 1 with 0, because we have to have a two-way bi-directional relationship here. Okay, so after doing that, we have made our adjacency list. Now what we are doing here, we are basically calculating the number of leaves node in that adjacency list. So leaves nodes, you remember, we have as I have shown you here, all the leaf nodes had size only 1, that like this. 6 has 5 only, 7 has only 0, 9 has only 1, right? So here every leaf node has only one size, because there is only one edge. So same way, because we have only one way, that is why I'm checking that whoever has the size equal to 1, those are basically our leaf nodes. So I'm adding them leaf nodes here into that adjacency list. Now I have made a remaining node variable, which initially need having the n as the value. I will show you why it is needed. Now see here, what I am doing here, while remaining node is greater than 2, means till the time we have more than 2 nodes, we are keep on removing the leaf nodes. So see here, remaining nodes equal to leaves dot size. So whatever leaves nodes we have calculated here, I'm just deducting the size. Okay, now once we are removing the new leaf node, we are removing the older leaf nodes, we get the new leaf nodes, right? So I can show you here. Once we delete 7, then 0 is new leaf node. If we delete 6 and 3, then 5 is new leaf node, right? So after deleting certain leaf nodes, we get some new leaf nodes as well. So for that part, I have written this logic. So after removing this, we have the new set of leaf nodes, right? So what I'm doing here is, whatever leaves we calculated here, we have to delete it from the adjacency list. So here you can see every adjacency list, every adjacency list has the hash set, right? We have the n size adjacency list of the hash sets. So I'm getting just that variable which we gonna delete. So see here, because x is in our leaves, so I have to delete in that adjacency list whatever number is there, right? So I'm just getting the value to delete. Okay, then I'm going to that particular adjacency list and removing this to delete node. And similarly, we have to delete it from the to delete adjacency, because two-way direction we have to remove. Just like we added two-way direction, same way we have to delete also in the two-way. Now at the right after deleting, we should check whether is there something new which has the again this size equal to 1. So then this would be our new leaf. So I'm parking those new leaves in this array list, because we don't have to calculate again every time using a for loop, because as soon as something is deleted, there are the fair chance that something, if possible, might be a new leaf node. Okay, so after doing this, I am getting the new leaf nodes, a set of new leaf nodes, and then I'm assigning that new set of leaf nodes to that leaves variable which we initially calculated here on line number 27. Okay, so after assigning, see here again our while loop will come here. So we will check if remaining node is still greater than 2, then again we will deduct the same way, remaining size and leaf dot size, and then I'm making this new variable similarly, and then we're gonna delete all those leaf nodes here, And when we are deleting, at the same time we are also adding the newly created leaf nodes. So here on line number 42 I am checking, is there something newly become a leaf? If it is there, I am adding that here. And then same way till the time it is greater than 2. Once it is equal to 2 or less than 2, we are coming out of it. And those leaves basically would have all those guys, which would be our answer, which we just discussed. So this is the way. So now to better understanding, I would be highly suggest you take your pen and paper, do some dry run. Okay, then only it will make a great sense. Just watching the video would not make greater sense. So thank you for watching this video. Let me run as well this code, though I have already checked, so it would be run only. So if you have any concern, you can definitely make the comment. I would be come back to that. Thank you for watching the video.